Hello students, welcome to All Force e-learning channel. This is K. Nageshwar Rao, your physics faculty. Today we are dealing with session number 87. In the last session we have discussed about few problems and resistance connected details were discussed. Conductance, what is conductance, what is conductivity. Okay, conductivity, for conductivity one equation was derived. So those are the details that we have discussed in the last session. So today in this session, in session number 87, let us continue with a few other details connected with resistance. I'll go with the combination of resistances. See children, combination of resistance is something that you cannot actually ignore. Combination of resistances is connected with several other things. When you deal with circuital problems, you actually need to have awareness about how to identify a given set of resistors as in series combination or as in parallel combination. You have to identify. Unless you are able to identify whether they are in series and whether they are in parallel combination, sometimes you may not be able to handle the problem. So it's this knowledge is required. Okay, so let us continue with the combination of resistances. I'll continue with first series combination. Actually, two possible combinations are there: series combination and parallel combination. Series combination. Series combination. You say that whatever resistances were given to you, you say that those are in series combination if the same amount of current is passing through those resistances and same potential difference exists across the entire combination of those resistances. If these two conditions are fulfilled, you can say that those given resistances in the circuit are in series. What are those two conditions? Same amount of current should pass through all the resistances, and across the combination same potential difference should be given in the circuit. Then you can say that the combination is series combination. Okay, so let me take three resistances. Let us say one is R1, R2, and the other one is R3. Okay, you can take any number of resistances. You can go up to n number of resistances. Okay, let us say one battery is connected in the circuit like this. A current I is flowing through the circuit, and let potential difference is applied to this combination by the battery is V. Let us assume like that. Okay, so what's the situation? You say that these three resistances are in series combination if same amount of current is passing through all these resistances, right? Now resistance, R1 value is different, R2 value is different, R3 value is different. It's not like that they should be always different. They can be same also, but if at all if I consider that these three resistances are different, it means let us say if R1 is offering less resistance when compared to R2, it means for the passage of electrons, for the passage of charge through this resistance, less opposition is offered by the resistor when compared to this one. So here more resistance is offered to the passage of the electrons, to the passage of the charge. It means the potential difference. See, what is driving this charge? Potential difference is driving the charge, isn't it? Potential difference is the one which is driving the charge. Here more resistance is present, so more hindrance will be there for the passage of the electrons. So you need more driving force, or you need more potential difference here, and here comparatively small potential is required if R1 is less than R2. So all that you need to understand is when you take different resistances in the series combination, across each resistance potential drop will be different. But whatever it is, when you add all those potential drops, you will get this V, because this is what gets distributed across these resistances. Whatever potential is supplied by the battery, that's what gets distributed across the given three resistors, isn't it? Let me assume that potential drop across this R1 resistance is V1, potential drop across this R2 is V2, potential drop across this R3 is V3. Okay, now if I wanted to write expression for this V1, how it can be written? V1 can be written as, according to Ohm's law, V is equal to IR. How much is the current passing through this one? How much? I is the current passing through this all three resistances. So I into what is the resistance of this resistor? R1. V1 is equal to IR1. Similarly, what you can write? V2 is equal to IR2 and V3 is equal to IR3. This is how you can write, isn't it? Now when you add all these potential drops, what you will get? You will get this V. So V is equal to, therefore V is equal to V1 plus V2 plus V3. What is V1? V1 is I into R1 plus I into R2 plus I into R3. What about this V? This is what? Total potential. In terms of Ohm's law, total potential can be expressed as total current into total resistance. What is the total current in the circuit? I only. We don't know what is the total resistance offered by the circuit, isn't it? That's what our primary goal is. We wanted to find out how much is the resistance offered by this combination, isn't it? I will assume that resistance offered by this series combination is Rs. So this Rs is what? Total resistance offered by the circuit. This I is total current flowing through this one. When you multiply these total values, what you will get? You will get total potential drop, isn't it? Now see, on RHS side and on LHS side, I is there common, right? You can cancel it out, and what you will get finally? Rs is equal to R1 plus R2 plus R3. So it's that simple. When you take several resistances in series, the effective resistance offered by the circuit will be R1 plus R2 plus R3. If you take n number of resistances, R1 plus R2 plus and so on Rn. Okay, so simply you need to add all the resistances, then you will get effective resistance offered by the combination. Okay, so this is what the conclusion is. I'll discuss a few other points connected with this one. For example, if I wanted to find out potential drop across the first resistance V1, how it can be done? Let us see. Okay, what is the first conclusion? Effective resistance conclusion. The next one, let me try to find out what is the potential drop across V1. Because here known values will be like R1, R2, R3, I, V, these things are known to us, isn't it? Rest of the things are not known to us. So let us find out V1 in terms of known quantities. So V1 is equal to, how it can be written from this equation, I into R1, isn't it? And this current I can be written as V is equal to IR, I is equal to V by total resistance. Here this is what total current in the circuit. Total current in the circuit is equal to total potential drop divided by total resistance of the circuit. Total resistance of the circuit is how much? Just now we have derived R1 plus R2 plus R3. So write it here, R1 plus R2 plus R3 into R1, isn't it? Similarly, you can write V2 as IR2 and similar kind of equation, except in the numerator you will have R2 by R1 plus R2 plus R3. Like that you can write expression for V3 as well. V3 is equal to IR3 VR3 by R1 plus R2 plus R3. Okay, so that's how potentials can be calculated. Now look at this picture. Whatever effective resistance we have, equation we have obtained, this indicates that the total resistance offered by resistances which are in series combination is greater than the greatest value of all these resistances. For example, if you have taken 1 ohm resistance here, 2 ohms resistance here, 3 ohms resistance here. Among these 3 resistances, which is the largest value? 3 ohms is the largest value. When you go with the effective resistance offered by this combination, 1 plus 2 plus 3, which is equal to 6. 6 is greater than the greatest value of the combination. What is the greatest value of the combination? 3 is the greatest value of the combination. So whatever total resistance offered by the circuit is there, it will be always greater than the larger value in the combination. Remember this point. So these are the details that you can handle, you can remember in connection with the series combination. The other one is sometimes you will be asked conceptual questions like what is the ratio of potential differences across the resistances connected in the series combination. You can find out that easily. Ratio in the sense you can take it like this. V1 is to V2 is to V3. How it can be written? V1 is to V2 is to V3. IR1 is to IR2 is to IR3. I gets cancelled, so R1 is to R2 is to R3. So the ratio between potential drops across resistances is equal to what? Ratio between resistances. Okay, so these are a few points connected with the resistance. Now, what if you are interested to calculate the effective resistivity offered by the circuit? Already we are aware of resistivity data as well, right? Resistivity, electrical resistivity, R is equal to rho into L by A. There we have come across resistivity, isn't it? So let us try to find out effective resistivity offered by the circuit if you go with this kind of series combination. I will assume that resistivity of this wire is I'll take it as rho 1, and resistivity of this wire I will take it as rho 2, and resistivity of this wire I will take it as rho 3. Okay. Now let me erase this part. See, what is rho 1? Rho 1 is equal to, let me write first what rho is. Okay. rho is equal to R into A by L. In fact, R is equal to rho into L by A. So from there, I shuffled the equation and I have written equation for rho. Now, if I wanted to rho expression for rho 1, resistivity of the first resistance, rho 1 can be written as R1 into A by L1. See, since we are going with the series combination, we have to, we will assume that we have taken what all the wires of same cross sectional area. So I'll take area same everywhere, okay, and lengths are different. I'll assume like that. Lengths are different. L1 is the length of the first resistance. See, resistance in the sense here, I am assuming that just few wires are connected. See, usually standard resistances are available in the laboratories. Okay, while doing this kind of experiments, you can use those resistances, or simply you can take any wire and you can find out resistance offered by that wire. Okay, so let us assume that here three wires are taken. So the second wire's resistivity, I'll take it as rho 2, which is R2A by L1, isn't it? And the third one is rho 3, which is R3A by, sorry, this is L2, this is L3. Okay, so these three lengths are different. Now, I'll make use of this equation. Okay, the effective resistivity, I will write it like this: rho effective is equal to R effective series combination. This here also, this is subscript S indicates that we are dealing with the series combination. A by the total length. Total length is how much? L1 plus L2 plus L3, isn't it? Now, I will make use of this equation. Rs is equal to R1 plus R2 plus R3 is there. No, this has been already derived. So, from this equation, I will write what R1 is and I will substitute here. And from this equation, what is Rs? Rs can be written as rho s into L1 plus L2 plus L3 by A, isn't it? So, I will replace Rs with rho s into L1 plus L2 plus L3 by A is equal to R1 can be replaced with rho 1 L1 by A, rho 1 L1 by A, plus R2 is rho 2 L2 by A, plus rho 3 L3 by A. So, here you can take out A common and you can cancel it out, and finally rho s comes out to be rho 1 L1 plus rho 2 L2 plus rho 3 L3 by total length L1 plus L2 plus L3. So, that is how you can talk about effective resistivity, and inverse of this will be what it gives us effective conductivity. Of course, individually also you have to take inverse, then you have to proceed in the same way, and you can get the effective value of conductivity as well. Let us talk about one of the possible situation here. Let L1 is equal to L2 is equal to L3, all are of same length. I'll take it as L. Then what happens? This rho s can be simplified as rho 1 L plus rho 2 L plus rho 3 L divided by L1 plus L2 plus L3. So all are L's only. So you will have 3L, and you can take out L common from the numerator, and numerator L and denominator L gets cancelled, and finally you are left with rho 1 plus rho 2 plus rho 3 by 3. So this is what effective resistivity in the series combination. So these are few details that you should remember. Okay, when we start working with the problems, okay, in the next later sessions, we'll make use of these details, okay, and we'll try to solve problems. Okay, so I'll continue with the parallel combination. This is what series combination. Now I'm going to continue with parallel combination. Parallel combination. Okay, I'm going to take 3 resistors like this. This is what this is how we represent the resistance. Okay, let the resistance of this resistor is R1, R2, and here it is R3. Okay. Now I'll connect one battery across this combination like this. Let the potential supplied by the battery is V. Let the total current passing through the circuit is I. What is parallel combination? See, you say that the given resistances are in parallel combination when same potential exists across all the what resistors, individual resistance. Whatever potential you are supplying, if that is across individual resistances, if the same potential difference exists, if same potential drop exists, okay, individually, okay, across this one, across this one, across this one, if same potential drop exists, then you can say that the combination is parallel combination. And here, unlike in the previous case, currents won't be same through all the resistances. Here this is not series combination, right? So whatever current is reaching this point, it gets bifurcated into three parts, and let us say this is I1, this is I2, and this is I3. So like that, current gets bifurcated and it enters into these three branches. So how much value of current passes through a particular branch, it depends on resistance offered by the branch. Okay, if resistance offered by these three branches is same, then same amount of current, this I gets divided into I by 3, I by 3, I by 3. So like that, it gets divided equally and it passes through three branches if all the resistances are same. Okay, so this is the circuit. Let us proceed with the effective resistance equation. Okay, here I, whatever current is there in the total circuit, that current I can be written as I1 plus I2 plus I3, isn't it? From Ohm's law, I can be written as V by R. This total current can be expressed as total potential divided by total resistance of the combination. I will take total resistance of the combination as R subscript P, parallel combination, no, is equal to I1. What is the potential across I1? I1 in the sense the first resistance. Potential across first resistance is also V only. So V divided by resistance offered by this first resistance is R1 plus, similarly I2 is V by R2 plus I3 is V by R3, and V gets cancelled on both the sides, and finally you are left with this equation 1 by Rp is equal to 1 by R1 plus 1 by R2 plus 1 by R3. So this is what gives us the effective resistance offered by this circuit in the parallel combination. Okay, I'll consider that only two resistors were taken in the circuit. Okay, so that we'll be able to have a simpler equation. So let two resistors are taken in the circuit. Therefore, 1 by Rp can be written as 1 by R1 plus 1 by R2. 1 by R1 plus 1 by R2. It can be simplified like this. Rp is equal to R1 R2 by R1 plus R2, isn't it? So this is what equation for effective resistance offered by the parallel combination of two resistors. Now let us find out what the values of I1 and I2, I3 are. I1 can be expressed as, I1 is written here as V by R1, right? So I1 is equal to V by R1, isn't it? And this V can be written as, V is what? Total potential. Total potential is equal to total current in the circuit into total resistance offered by the combination divided by R1. That's how you can write the equation. And what this Rp is, if you have taken only two resistances, Rp can be written as R1 R2 by R1 plus R2 into, in the denominator here one R1 is present, and this R1 gets cancelled, and finally I R2 by R1 plus R2. So that is the current passing through the first branch. This is when you have taken only two resistances. Okay. Through the second resistance, current passing will be V by R2, which is equal to, similarly we will proceed, and you can guess what we are going to get. If you are taking I1, you are getting IR2 by R1 plus R2. So denominator part is common. Okay, so in the numerator, what you will get here? You will get R1. So I into R1 by R1 plus R2. So that's how you will be able to identify individual currents traveling through the branches. Now, let us talk about ratio between these currents. I1 is to I2 is to I3. Okay. Or simply, since we have already picked up example of a network having two resistances, I will confine my discussion to only two resistors. I1 is to I2 is equal to, I1 can be written as V by R1, right? So V by R1 is to, I2 is V by R2. V by R1 is to V by R2. Now VV gets cancelled, so finally what you are left with, 1 by R1 is to 1 by R2. So I1 is to I2 is equal to 1 by R1 is to 1 by R2. If you have taken three resistances, I1 is to I2 is to I3 will be 1 by R1 is to 1 by R2 is to 1 by R3. That's how you'll be able to talk about the ratio between the currents. Okay, so there are similarities between the series combination and parallel combination. There our focus was on V1, V2, V3 because that's what observed to be different across the three resistances. Okay, sometimes it can be equal. If resistances are same, potential distribution will be same in series combination, right? So here I1, I2, I3, these are the different values connected with the individual resistances. There in series combination, V1, V2, V3 are different values connected with individual resistances. So here our focus is on currents, and there in series combination our focus was on potentials, isn't it? And we can talk a little bit more. In series combination, I told you the effective value of the series combination is always greater than the greatest value of the combinations. And here, unlike in the case of series combination, here the effective value will be smaller than the smallest value of the combination. For example, if you have taken 1 ohm resistance, 2 ohm resistance and 3 ohm resistance, when you go with the calculation, let us say I have taken, let me calculate, R1 is equal to 1 ohm, R2 is equal to 2 ohms. So Rp is equal to R1 R2 by R1 plus R2. So 1 into 2 by 1 plus 2. So you will have 2 by 3, which is equal to how much? 0.66, isn't it? So here this Rp is less than 1. The effective resistance offered by the parallel combination is less than 1. 1 is what? Smallest value of the combination. So you have taken 1 and 2, which one is smaller? 1 is smaller, and whatever effective value you are getting, that is smaller than the smallest value of the combination. So unlike in the series combination, here the effective resistance offered by the parallel combination will be smaller than the smallest value of the combination. Okay, so wherever when you do any experiment, sometimes you may not be having all kinds of resistances with you. What you can do, if you need some 10 ohm resistance, for example, you are having 5 ohms resistances only. So then what you can do, you can go with a series combination of two 5 ohm resistances. 5 plus 5, it gives us 10, isn't it? Like that, you can make use of knowledge of this combination of resistances to generate whatever kind of resistance you wanted to use in the experiment. Okay, so these are few fundamental details connected with the combination, and we can go with the resistivity also here as well. What you can do is, I'll do that. Let me continue with the resistivity part. I will assume that in the circuit two resistors are taken like this. A battery V is connected, R1, R2, I1, I2. Okay. So now R1 in terms of resistivity can be expressed as rho 1 L by A1. Here the lengths of resistances are same, but cross section areas you can have different. You can have different cross sections can be taken, because current entering is different, no? So you can have different cross sections, no problem. Okay, and R2 can be expressed as rho 2 L by A2. Therefore 1 by Rp. Let me talk about Rp also. Effective resistance of the parallel combination, Rp can be written in terms of resistivity as rho P, parallel combination related effective resistivity, into L by what is the total area into which this current is entering, A1 plus A2. That's how you can consolidate the data connected with the resistivity. So what is Rp? Rp is equal to, or I'll make use of this equation, 1 by Rp is equal to 1 by R1 plus 1 by R2. So 1 by Rp can be written as A1 plus A2 by rho P into L is equal to 1 by R1, inverse of this one, A1 by rho 1 L plus inverse of this one, 1 by R2, A2 by rho 2 L, isn't it? Now, on both the sides, L is there and you can cancel that. So, when you cancel that, what you will get? You will get A1 plus A2 by rho P, A1 plus A2 by rho P, L got cancelled, and on the other side, RHS side, you will have A1 by rho 1 plus A2 by rho 2. Now, A1 rho 2 plus A2 rho 1 by rho 1 rho 2, A1 plus A2 by rho P. So, take inverse of this, or you can write rho P as rho P is equal to rho 1 rho 2 into A1 plus A2 by A1 rho 2 plus A2 rho 1, isn't it? So, this is what the equation for effective resistivity of the parallel combination of two resistors. This is how you can write. What if areas are equal? Let A1 is equal to A2 is equal to A. If this is the situation, rho P gets modified like this, rho 1, rho 2, A1, A2 both are same. You can write it as 2A by A can be taken out common, you will have rho 1 plus rho 2. A gets cancelled. So, finally, we are having 2 rho 1 rho 2 by rho 1 plus rho 2, which is nothing but effective resistivity of the parallel combination when both the cross sections of the wires are same. And you can replace these resistivities with in 1 by sigma. What is sigma? Conductivity. Okay, and you can find out the expression for effective conductivity as well. Okay, so these are some details about the combination. Now let us deal with the resistance a bit more. Now let us discuss about temperature dependence on what resistance. Okay, temperature dependence of resistance. Temperature dependence of resistance. We all know that if the temperature is raised for a conductor, the resistance increases. I told you the reason in the previous sessions. When temperature is increased, the thermal kinetic energy gained by the electrons increases, and even atomic sites also they undergo vibration. So there will be frequent collisions between the flowing charges and the atomic sites, and several other factors gets influenced. Average time, drift velocity, all these things gets influenced, and rate of collisions, number of collisions taking place per unit time will increase. If number of collisions per unit time increasing, what does it mean? Resistance offered by the conductor is also increasing. So you should remember this fact forever. When temperature is raised, what is happening to the resistance? Resistance is increasing. But the question is, when we go very deep into this temperature connection with the resistance, it will be different at different temperatures. Like in first year we talk about specific heat. At different temperatures it will have different values, isn't it? There will be slight variation. Okay, though we treat it as constant, but here also, what if I am dealing with room temperatures? Let us say the temperature of the conductor is raised from 50 degrees Celsius to some 80 degrees Celsius. So how much is the rise in temperature? 30 degrees Celsius. Now what if I raise the temperature from 500 degrees Celsius to 550 degrees Celsius? Or 530 degrees Celsius, 500 to 530. In the previous case, 50 degrees Celsius to 80 degrees Celsius. How much is the rise in temperature? 30 degrees Celsius. And in the second case, what I am talking about, raising the temperature from 500 to 530. In both the cases, rise in temperature is same, but the rise in resistance may not be same, because at higher temperatures the scenario will be, it can be different, because you are dealing with high temperatures. When you are dealing with a high temperature and randomness, random motion of the free electrons, that's something that you cannot actually control. Okay, so that increases abnormally. The scenario will be different. Okay, so here when we study about the temperature's effect on the resistance, we study under two different parts. One is, what if you are dealing with conductors below 300 degrees Celsius? What if you are dealing with conductors having temperature more than 300 degrees Celsius? Okay, so under these two categories, we can make a study. I'll assume that let R naught is resistance at 0 degrees Celsius and RT is resistance at T degrees Celsius. Okay. Now, if T is greater than 300 degrees Celsius, T is what? Greater than 300 degrees Celsius. See, why we are much interested in 300? See, these kind of conclusions are drawn after making several experimental observations. Okay, so this is what a number can be taken as a reference. That's what we have come to know. Okay, so if T is greater than 300 degrees Celsius, then this RT can be expressed as RT equal to R naught of 1 plus alpha T plus beta T square, and where alpha, beta are called temperature coefficients of resistance, temperature coefficient of resistance. Now what this equation is, all of a sudden how come this equation is realized here? See, in physics we deal with the two kinds of equations. Equations which are having a reasonable base with the theory, like you will have a theoretical proof, and there are equations which are actually called as empirical relations. Empirical relations in the sense, just by bare observations, by taking a few scientific bases, you will come to such kind of conclusions. So you can treat this as one such kind of equation at this moment at your standard. You can consider this equation something like that. Okay, so out of several observations, this is what we can identify. RT, temperature at resistance at a temperature T, can be written as resistance at 0 degree Celsius into 1 plus alpha T plus beta T square, and alpha beta are called temperature coefficients of resistances. Temperature coefficients of resistance. These are constants for a given material, of course. But when you change the temperature, of course, it too they too will change. Now look at this equation. So here, and when the temperature is increasing, even from this equation also, what conclusion we can draw? Yes, resistance increases. What if you are dealing with temperature less than 300 degrees Celsius? In this case, RT can be written as R naught of 1 plus alpha T. Okay, no need to have this one. Now let us compare these two equations. At higher temperatures, what do we expect? We expect the resistance of the conducting material to rise abnormally. And when it is changing abnormally, when it is increasing abnormally, this T term, alpha into T, whatever this T is there, this may not be sufficient to deal with the situation. So that T square is also introduced, so that overall rise in resistance can be put it in the form of in an equation. Okay, when it is less than 300 degrees Celsius, when you are maintaining the conductor at less than 300 degrees Celsius, this equation is sufficient. This T will take care of rise in resistance. Okay, and from this equation also you can draw several conclusions. If you want to write expression for alpha, how it can be written? In fact, RT is equal to R naught plus R naught alpha T, isn't it? From here, alpha can be written as RT minus R naught by R naught T, isn't it? This is the expression for temperature coefficient of resistance. If at all, if you are not dealing with 0 degrees Celsius, here to be more precise, this T in place of T, you will have delta T. Delta T in the sense, the difference between the two temperatures. Here, what are the two temperatures that we are dealing with? 0 and T. So T minus 0 will be T. So that it was written as T here. Okay. These details are a little bit connected with first year. In first year, you have come across linear coefficient of expansion, areal coefficient of expansion, volume coefficient of expansions, isn't it? So these details are slightly connected with the format, how they appear in first year, isn't it? Okay, now let us talk about one more situation. Let us say at a temperature, at a certain temperature, resistance is R1, and that R1 I am expressing it as R naught into 1 plus alpha T1. At a temperature T1, resistance is taken as R1. At a temperature T2, let the resistance is R2 is equal to R naught of 1 plus alpha T2. These are the two equations. Let me draw a conclusion. I'll take ratio between these two equations. R1 by R2 is equal to R naught gets cancelled. You will have 1 plus alpha T1 by 1 plus alpha T2, and take cross multiplication. R1 plus R1 alpha T2 is equal to R2 plus R2 alpha T1. So from here what you can write, R1 T2, I'm bringing this term towards LHS side, minus R2 T1 alpha, it can be taken out, and this R1 is taken towards RHS side, R2 minus R1, R2 minus R1. So from here, temperature coefficient of resistance alpha can be expressed as R2 minus R1 by R1 T2 minus R2 T1. This is also another equation when you are dealing with numerical problems based on resistance at two different temperatures, so T1 and T2, you can make use of this equation to find out temperature coefficient of resistance. Okay, so these are few details. Let us talk about resistivity part also. You know, when you write equation for resistivity equation also appears something like this only. Okay, you can directly just you can have one idea about temperature coefficient of resistivity also. Okay, temperature dependence of resistivity. So here at T1 and T2 are two temperatures that we are dealing with the in this situation T2 is greater than T1. Okay, therefore we have to define resistivities as well, right? So resistivity corresponding to this temperature T1, I will take it as rho 1, corresponding to this T2, I will take it as rho 2. This rho 2 can be expressed as what alpha into rho 1 into 1 plus alpha into T2 minus T1. So that's how we can write the expression for resistivity at a temperature T2. Okay. Now let us talk about a few other details connected with the resistivity. I'm going to draw a graph corresponding to conductors and alloys and semiconductors, and let us see what happens, how resistivity changes with the temperature. Let us try to understand that. Let us say this is the graph. I have taken temperature on this axis, temperature, and this axis is resistivity. Okay. For conductors, when the temperature is increasing, what happens to the resistivity? Resistivity increases linearly. This is how you see the variation of resistivity of conductors with the temperatures. Conductors. Okay. And for semiconductors, it will be something like this. It will be something like this. It decreases. It decreases because I have given you explanation in the previous session. There won't be any availability of electrons. When you raise the temperature, actually, it starts taking part in the conduction of electricity. So, if electricity is, if it is able to conduct the electricity, then what do you say? You say that resistance has decreased. I mean, till that time, it is not conducting any electricity. When the temperature is raised, the availability of free electrons for the conduction of electricity has increased. So, logically, what you can conclude? You can conclude that its resistance is decreasing. So, when the temperature is increasing, what happens to the resistivity of semiconductors? Semiconductors. I will change the position of this axis. I will take position of the axis somewhere here. Okay. Now, along this line, you can have one more category of materials. If I have drawn a straight line, what does it mean? Though the temperature is increasing, the resistivity is not increasing, isn't it? Temperature is here. So what is happening for this category of materials? Temperature is increasing, but resistivity remains constant. These kind of materials are, you can call them as alloys. When you go with alloys, we'll have a combination of materials, isn't it? When you go with a combination of materials, there will be, arrangement of the atoms inside the material will be random. When they are randomly arranged, by default, they already possess, some kind of resistance, and that will be the highest value, when compared to rest of the things like conductors and semiconductors. When you are dealing with the maximum possible value of resistivity, though there is a change in temperature, that maximum value doesn't change. So for alloys, you will have this kind of line. Not for all alloys. To be more precise, manganese and Constantin. So these two alloys, manganese, it's made up of manganese, copper, and nickel, whereas Constantin, copper and nickel. Okay, so for these two materials, it almost remains constant resistivity. Approximately, it remains constant when the temperature is changing. So it's like completely it is immune to temperature. It doesn't fluctuate. Okay, so because of this reason, we use these materials to manufacture standard resistors. Okay, when you are dealing with standard resistor in laboratory, if there are temperature fluctuations, when you switch on the AC or in hot summer day, if you are doing some experiment without using any AC, what happens from morning to afternoon, there will be rise in temperature. So that rise in temperature, if it can influence the resistance, whatever resistor you are using, then what happens? You will be in trouble. We will not be able to see some kind of systematic data, isn't it? So these kind of materials are used which are completely, almost completely immune to temperature fluctuations. Their resistivity remains constant. The reason is they were already having randomness. Degree of randomness is more when you take alloys. Okay, so they were already having high values of resistivity. So if they were already having high values of resistivity, though you change the temperature, there won't be much change, isn't it? So at this point of time, you can talk about the relation between resistivities of these three kinds of materials. So resistivity of alloy will be always greater than resistivity of semiconductor will be greater than resistivity of conductors. These details will help us to to face conceptual questions in the examination. Okay, so these are the details about resistance and resistivity.